The 1999 Electric Code, also known as the National Electrical Code or NEC, mandates the installation of 20 feet of bare or coated reinforcing bars within and near the bottom of a concrete foundation or footing. The primary purpose of this requirement is to establish a continuous electrical grounding path that connects the electrical system to the earth. This grounding path is crucial for safety, as it provides a low impedance route for fault currents to return to the source, thereby facilitating the operation of overcurrent protective devices like circuit breakers and fuses. These devices then interrupt the circuit, preventing electrical shock hazards and minimizing the risk of fire. The code doesn't explicitly define where the rebar must be located within the concrete. The intent is to ensure adequate contact with the earth through the concrete and the reinforcing steel. He raised the question of whether installing 20 feet of rebar, with 3 feet exposed above the footing, meets the NEC code requirements. The interpretation is that yes, the installation of 20 feet of rebar with 3 feet exposed above the footing satisfies the intent of the NEC code. The National Electrical Code does not specify precisely where the rebar should be positioned within the concrete. Consequently, having a portion of the rebar extending above the footing is permissible. The exposed segment of the rebar will still contribute to the electrical grounding path, considering it's connected to the grounded electrical system. The 3-foot exposed section of the rebar facilitates convenient access for connecting grounding wires originating from the electrical system. The NEC focus is on achieving effective grounding, and the described installation method aligns with this objective. Here's a more detailed breakdown of why this installation is compliant with the code and a look into the practical considerations involved. Firstly, the primary goal of a concrete encased electrode, often referred to as a U for ground, is to provide a reliable and low-resistance connection to the earth. This is achieved by embedding the reinforcing steel within the concrete, which acts as a conductive medium. The concrete itself is in direct contact with the earth, allowing for a large surface area through which fault currents can dissipate. The 20-foot requirement is based on empirical data and engineering principles, which have demonstrated that this length is generally sufficient to achieve an adequate ground resistance in most soil conditions. Secondly, the NEC doesn't mandate that the entire 20 feet of rebar must be completely encased in concrete. The phrase within and near the bottom allows for some flexibility in the installation. The key is that the majority of the rebar should be within the concrete to ensure good contact and effective grounding. Having a portion of the rebar exposed doesn't negate the effectiveness of the overall grounding system, as long as the remaining portion is adequately encased. Thirdly, the exposed portion of the rebar serves a practical purpose by providing a convenient point for connecting the grounding electrode conductor, also known as the GEC. The GEC is the wire that connects the grounding electrode to the electrical service equipment, such as the main panel. By having a portion of the rebar exposed, it simplifies the process of making a secure and reliable connection. This is particularly important because the connection must be able to withstand corrosion and mechanical stress over time. Fourthly, it's crucial to ensure that the connection between the GEC and the rebar is made using approved methods and materials. Typically, this involves using a listed grounding clamp or connector that is specifically designed for this purpose. The connector should be made of a material that is compatible with both the rebar and the GEC to prevent galvanic corrosion. The connection should also be protective from physical damage and environmental factors. Fifthly, when installing a concrete encased electrode, it's important to consider the size and type of rebar being used. The NEC specifies that the rebar must be at least 1/2 inch in diameter. This is to ensure that the rebar has sufficient mechanical strength and current carrying capacity. The rebar can be either bare or coated with zinc or another electrically conductive material. The coating is primarily for corrosion protection and doesn't significantly affect the grounding performance. Sixthly, the concrete mix design can also impact the effectiveness of the grounding system. The concrete should have a low water to cement ratio to minimize its resistivity. The concrete should also be properly consolidated to ensure good contact with the rebar. In areas with particularly poor soil conditions, it may be necessary to use a concrete admixture to further reduce its resistivity. Seventhly, it's important to note that a concrete encased electrode is just one type of grounding electrode that is recognized by the NEC. Other types of grounding electrodes include ground rods, ground plates, and metal underground water pipes. In some cases, it may be necessary to use multiple grounding electrodes to achieve an adequate ground resistance. The choice of grounding electrode depends on the specific site conditions and the requirements of the electrical system. Eighthly, the NEC requires that the ground resistance of the grounding system be tested to ensure that it meets the code requirements. The ground resistance should be measured using a ground resistance meter, also known as a ground tester. The ground resistance should be low enough to allow for the effective operation of overcurrent protective devices. If the ground resistance is too high, it may be necessary to install additional grounding electrodes or improve the soil conductivity. Ninthly, it is imperative to adhere to the specific requirements outlined in the NEC and local electrical codes. The electrical codes are designed to ensure safety and proper functioning of electrical systems. Ignoring these codes can lead to dangerous situations, including electrical shocks, fires, and equipment damage. Always consult with a qualified electrician or electrical engineer to ensure that your electrical system is installed and maintained in accordance with all applicable codes and standards. Tenthly, while the 3-foot exposure is generally acceptable, it's important to consider the specific environmental conditions at the site. In areas with high levels of corrosion, it may be necessary to provide additional protection to the exposed rebar. This could involve coating the rebar with a corrosion-resistant material or enclosing it in a protective sleeve. In areas with heavy foot traffic, it may be necessary to protect the exposed rebar from physical damage. 11thly, the installation of a concrete encased electrode should be carefully documented. This documentation should include the location of the electrode, the type and size of rebar used, the method of connection to the GEC, and the results of the ground resistance test. This documentation will be helpful for future maintenance and troubleshooting. 12thly, it's important to remember that grounding is just one aspect of electrical safety. Other important safety measures include proper wiring techniques, the use of ground fault circuit interrupters, and regular inspection and maintenance of electrical equipment. By following all applicable codes and standards and taking appropriate safety precautions, you can minimize the risk of electrical hazards. 13thly, in summary, the installation of 20 feet of rebar with 3 feet exposed above the footing is generally acceptable and satisfies the intent of the NEC code for providing a continuous electrical grounding path. The code doesn't specify exactly where the rebar must be located within the concrete. The exposed portion allows for easy access to connect grounding wires. Always ensure that the connection is made using approved methods and materials, and that the grounding system meets the code requirements. 14thly, grounding is an integral component of electrical system safety. It establishes a low impedance pathway for fault currents to return to the source, facilitating the swift operation of overcurrent protection devices like circuit breakers and fuses. This action curtails the duration of electrical faults, mitigating the risk of electrical shock and potential fire hazards. In scenarios where a metallic component of an electrical system, such as the chassis of an appliance or the enclosure of a piece of equipment, becomes energized due to an insulation failure of the fault condition, the grounding system provides a route for the fault current to flow back to the source. This surge in current triggers the overcurrent protection device, causing it to trip and energize the circuit, effectively disconnecting the faulty component from the power supply. Without a proper grounding system, the fault current may not be sufficient to activate the overcurrent protection device. This could leave the metallic component energized, posing a significant electrical shock hazard to anyone who comes into contact with it. Moreover, the prolonged flow of fault current can lead to overheating and arcing, increasing the risk of fire. 15thly, the concrete encased electrode, also known as a UV ground, is a type of grounding electrode that is specifically designed for use in concrete foundations and footings. It consists of a minimum of 20 feet of bare or zinc galvanized steel reinforcing bars, which are encased in concrete and connected to the building's electrical grounding system. The concrete encasement provides a large surface area for contact with the earth, resulting in a low resistance ground connection. 16thly, the NEC specifies the requirements for concrete encased electrodes in section 250.52. A3. This section outlines the minimum length and size of the reinforcing bars, as well as the requirements for the concrete encasement. The code requires that the reinforcing bars be at least 1/2 inch in diameter and that they be located within and near the bottom of the concrete foundation or footing. The concrete must be in direct contact with the earth and must have a minimum thickness of 2 inches. 17thly, in addition to the concrete encased electrode, the NEC also recognizes other types of grounding electrodes such as ground rods, ground plates, and metal underground water pipes. Ground rods are typically made of copper or copper-clad steel and are driven into the earth to a depth of at least 8 feet. Ground plates are typically made of copper or galvanized steel and are buried in the earth at a depth of at least 30 inches. Metal underground water pipes can be used as grounding electrodes if they meet certain requirements, such as being in direct contact with the earth for at least 10 feet. 18thly, the choice of grounding electrode depends on various factors, including the soil conditions, the size and type of electrical system, and the local code requirements. In some cases, it may be necessary to use multiple grounding electrodes to achieve an adequate ground resistance. For example, if the soil is particularly dry or rocky, it may be necessary to install multiple ground rods or a combination of ground rods and a concrete encased electrode. 19thly, the NEC requires that the grounding system be tested to ensure that it meets the code requirements. The ground resistance should be measured using a ground resistance meter, also known as a ground tester. The ground resistance should be low enough to allow for the effective operation of overcurrent protective devices. The specific ground resistance requirements vary depending on the size and type of electrical system. 20thly, it's important to note that grounding is not the same as bonding. Grounding is the process of connecting the electrical system to the earth, while bonding is the process of connecting the metallic parts of the electrical system together to create a low impedance path for fault currents. Both grounding and bonding are essential for electrical safety. Bonding ensures that all metallic parts of the electrical system are at the same electrical potential, which reduces the risk of electrical shock. 21stly, improper grounding can have serious consequences, including electrical shock, fire, and equipment damage. It's crucial to ensure that the grounding system is installed and maintained in accordance with all applicable codes and standards. Always consult with a qualified electrician or electrical engineer to ensure that your electrical system is properly grounded. 22ndly, the interpretation that the 3-foot exposure of rebar is acceptable assumes that the remaining 17 feet of rebar is properly encased in concrete and in direct contact with the earth. If the 17 feet of rebar is not adequately encased or if the concrete is not in direct contact with the earth, the grounding system may not be effective. 23rdly, in some jurisdictions, local codes may have more stringent requirements for concrete encased electrodes than the NEC. It's important to check with the local authorities to ensure that your installation meets all applicable requirements. 24thly, the long-term performance of a concrete encased electrode can be affected by corrosion. Over time, the reinforcing bars can corrode, which can increase the resistance of the grounding system. To minimize the risk of corrosion, it's important to use corrosion-resistant reinforcing bars and to ensure that the concrete is properly mixed and placed. 25thly, regular inspection and maintenance of the grounding system are essential to ensure its continued effectiveness. The grounding system should be inspected for signs of corrosion, damage, or loose connections. The ground resistance should be tested periodically to ensure that it remains within acceptable limits. 26thly, the NEC provides detailed guidelines for the installation, maintenance, and testing of grounding systems. It's important to familiarize yourself with these guidelines to ensure that your electrical system is properly grounded. 27thly, the primary function of grounding is to provide a low impedance path for fault currents to return to the source. This low impedance path allows for the quick operation of overcurrent protective devices, which minimizes the risk of electrical shock and fire. 28thly, grounding also helps to stabilize the voltage of the electrical system. By connecting the electrical system to the earth, Grounding helps to prevent voltage fluctuations and surges, which can damage sensitive electronic equipment. 29thly, in addition to providing a safety function, grounding can also improve the performance of electrical equipment. A properly grounded electrical system can reduce electrical noise and interference, which can improve the reliability and accuracy of electronic devices. 30thly, the NEC recognizes several different types of grounding systems, including the grounded system, the ungrounded system, and the impedance grounded system. The grounded system is the most common type of grounding system and is used in most residential and commercial buildings. The ungrounded system is typically used in industrial applications where it is important to maintain continuity of service. The impedance grounded system is used in applications where it is necessary to limit the ground fault current. 31stly, the choice of grounding system depends on the specific requirements of the electrical system. A qualified electrician or electrical engineer can help you to select the appropriate grounding system for your application. 32ndly, grounding is a complex and critical aspect of electrical safety. It's essential to understand the principles of grounding and to follow all applicable codes and standards to ensure that your electrical system is properly grounded. 33rdly, in conclusion, the interpretation of the NEC code regarding the concrete encased electrode allows for flexibility in the rebar placement. The 3-foot exposure, in this case, is acceptable as long as the rest of the installation adheres to the code requirements and maintains effective grounding. Always prioritize safety and compliance with electrical codes.